jūs visi tik kuplā skaitā šodienas atklātajā lekcijā. Prieks, ka ir tik daudz kognitīvo zinātņu interesantu. Šodienas runātājs ir profesors Goldstouns, kurš ir viens no šiem visietekmīgākajiem kognitīvu zinātniekiem šobrīd pasaulē. Veicis pētījumus gan uztveres jomā, gan arī vizuālās kognīcijas jomā, gan arī datorsimulāciju jomā un daudzās radniecīgās nozareis. Es domāju, mani ievadvārdi arī ar to varētu noslēgties. Kādā gadījumā priecāšos jūs redzēt arī parīt un aizparīt mūsu ikgadējā kognitīvo zinātņu simpozijā, un ar to dodu vārdu arī mūsu šodienas runātājiem. So I'm pleased and honored on behalf of the University of Latvia to give the floor to Professor Roberta Goldstouna.
So it's really my pleasure to be here. I want to thank the organizers, Jurgis and Edward and Jesse, for putting this all together. It's a great group of speakers that are going to be here over the next couple of days. Some of my heroes of cognitive science will be here, people I followed the work for years and years. It's really an exciting group of people. You should be proud of having these people here. I know that I'm proud to be part of it. And I'm extra proud that you're willing to be here instead of being outside now that spring has sprung in Riga. And so I'll try to make it worth your while. But it very well may be that you would have better spent this last hour outside on the river. So I'm going to be talking about percepts and concepts. And right off the bat, there's been an interesting move over the last couple of years in cognitive science, which would actually blur the distinction between percepts and concepts. Lynn Talmy has talked about cepts instead of percepts and concepts, and says there's really no difference between percepts and concepts. We should really be lumping them all together and just talking about cepts. Where can you draw the boundary between your basic identification, perceptual processes, and your deeper meaning-related processes? And this point has been raised again eloquently just this month in a book by Doug Hofstadter and Emmanuel Sander, who have talked purposely about talking about how the hallmark of human intelligence is the ability to make connections between events, perceptual events, but also conceptual events. They say intelligence to our mind is the art of rapid and reliable gist finding, crux spotting, bullseye hitting, nub striking, essence pinpointing. It is the art, when one is facing a new situation, swiftly and surely homing in on an insightful precedent or family of precedents stored in the recesses of one's memory. And this is nothing but the ability to find close analogs, which is to say, the ability to come up with strong and useful analogies. Right? And so it's quite impressive if you think about your everyday concepts, how they really are a blend between the perceptual and the deeper, more abstract essences that underlie them. And I could have taken lots of different concepts. Here are some concepts that are certainly among the first 300 words that a child will learn as they're developing. Things like nest and egg, tree, mom, son, ball. Consider the concept of string. It has both a very physical, perceptual aspect to it when you're talking about tying a box up with string, or you're talking about a string that wraps around a tree. But we also have varying degrees of extension of this concept that we all take for granted. We talk about stringing lights. We talk about a string of islands, even though there's no physical string there anymore. We talk about having a string of hit singles, right? Or a string of accidents. And in all of these cases, we know intuitively that string is the right word to use. So we can talk about a string of debates for presidency, but you would talk about the thread of arguments within a debate, or you would talk about roping somebody down within a debate, right? So we know what is the right extension for strings in this more extensive, abstract perspective, and we also know what these concrete strings are. And so we do this all without even thinking about it. So researchers in different parts of cognitive science have, interestingly, been getting at the notion of what is the extension of strings and other concepts in a way that both has its foot in the earth of perception and also one arm in the heaven of abstraction. So there's an apparent continuity of sieving, which is why Len Talmy wants to call it sieving rather than perceiving versus conceiving. You can think about a particular sieving event like your cat, identifying your cat, but you can also identify felines in general, mammals, animals, pets, predators, household members, dependents, individuals, agents, options, masses, objects of cathexis, units. So where can you draw a line and say, hey, this is no longer a perceptual process, this is just our higher order cognitive process? To many researchers, we shouldn't be interested in drawing that boundary. And it's interesting because there's a history of cognitive psychologists studying object perception who are interested in how to identify that that's a cat. And then there's other researchers who are interested in concepts, who are interested in saying, how do we categorize this thing as a cat? And it's turning out that many of the theories and mechanisms that have been postulated by one of these groups has been extended to the other group. And again, it's a point of unitization or combination between these groups. So some of the issues that I think we will be addressing over the next 2 or 3 days in the symposium all revolve around this generalized notion of septs that includes both what we perceive and what we conceive. One of the fundamental questions that's already been answered to us by Lynn Talmy in a negative is there a difference between perceiving and conceiving? And it's a difficult question on both eyes. If you say that there is a difference, then it becomes incumbent on you to say, what is that difference, right? But if there is no difference, then why does it seem like understanding or grasping different things seems to be so different? Understanding and logic, modus ponens, seems to be a very different process than just looking at a cat in the street and saying cat. So why, if there really is no difference between perception and conception, do they seem so different to us? And the next point is, well, if there is a difference, if there is no difference between perception and conception, then we don't have to address this, because you don't have to talk about how one thing can influence another thing if it's all the same thing. But for those people who think that perception is different from conception, then there is this question of how do concepts influence perception? And then, again, you have this choice point that if you say there's no influence between concepts and perception, then why do things look so different for people who have concepts that other people don't have? And one good example of this is the difference that expertise matters. So why do experts in a field seem to see things so differently than novices? Do different kinds of people really see different things? So it's been pointed out in many fields, including the sexing of day-old baby chicks, that experts seem to have very different perceptual apparatus that's been built up over 20 years for them. So they would instantaneously be able to say that all of the cloacal regions on the left are male and all of the cloacal regions on the right are female. Something that would be very hard to see for the rest of us. And the actual experts involve a lot of palpitating of the chicks. That's why the chick's identity is being anonymized. Right? That's good. So to protect its own identity. And there's mushroom experts who can easily distinguish Omphalos olearis from Cantharellus sabarius. I personally have confused the two, much to my gastrointestinal dismay. It goes up even higher and higher. So Mickey Chi and her colleagues have talked about, with science, how experts seem to organize their world of physics problems in a different way than novices, where novices will tend to group problems because they look alike superficially. These belong together because they all involve momentum or circular things or angular velocity, whereas the physicists are much more likely to group and naturally see resemblances between problems on the basis of the underlying physics law that they obey, like conservation of energy or second law of thermodynamics. Right? So this gives you an idea for the power of expertise to be able to connect things that would otherwise seem very dissimilar. And I think it's really our best hope for an educational system that we train our students to see the inferential power for thinking in terms of second law of thermodynamics, positive feedback systems, negative feedback systems, things that we would not normally think of categorizing our world in terms of, but they turn out to be inductively extremely powerful. To give you an idea maybe of what this expertise difference of perception looks like. See if this works. I've degraded a number of images, and I can create experts in you in just maybe 5 or 6 seconds. So hopefully some of you are having a hard time seeing what this is. And yet I can show you the undegraded view of it, and then instantaneously we'll be able to go back to this, and you'll have a hard time seeing it as it used to be, right? So actually you should treasure your virginal state now, because once I go back and show you what it is really a picture of, you won't be able to go back to seeing it the way you used to. Okay, so that's the undegraded picture. And now when we go back there, do you see it? So like this is part of her face, and that's just the background, right? So people are drawing lines, people are seeing connections that really aren't even there in the image. So this is her nose, I guess, but you can't really even see the nose in the bottom-up information in the image itself. Here's another example. Anybody see what it is? Yeah, right. So it's very specific. Not only are you seeing people, but you're seeing very specific people. C-3PO, right? I thought it was John Lennon, but yeah, it's C-3PO, and Princess Leia is in the foreground. You must be an expert. Yeah. So, right. So this is what the original scene looked like, and this is how it's been transformed. So this is really a different, well, two types of expert. I've made you all maybe some kind of level of expertise, although your level of expertise runs far deeper, to be able to see things when the information in the actual image far under constrains what you're going to be seeing. Okay, this is a hard one. Some people will be hallucinating things that aren't actually in the image. In this case, we know exactly what is in the image because I used Photoshop filters to degrade the images. Yeah? Oh, very good. Yeah. So that is a horse, right? So that was the original image, and this is the degraded version, right? And so what's impressive to me about this is that people will add boundaries that really are not there. And so you can tell this with perceptual psychophysical experiments, that people think of this over here as being a completely different object than this over here, but only when they've been turned into experts by showing the undegraded view of it. And here's one final example of this that I'll show you that I think is impressive because it is so striking. Once you see what it is, it looks like it's really photographic in its realism. but it's hard to see for many people. So this is actually a photograph of this object that you're looking at. But, oh, yep, somebody said it. Yep, it is indeed a cow. How many people see the cow? How many people only think they see the cow? Right, so here is the outline for the cow. If you could sort of, that's about where the cow would be, right? And so now you can go back and see it, right? And so that is, to some people, what it is like to be an expert. You're actually restructuring your perceptual world. So going back to our questions then, so this is maybe part of what we're trying to understand is how can our concepts really change, reach downwards to influence the very perceptual modules that are supposed to be founding them. And that relates to this question. If there is this influence of our concepts on our perception, then how is it possible that our perceptual apparatus is giving us the foundation for our concepts? It would seem to be a very shaky foundation itself if it's being buffeted around by the very thing that it's supposed to be founding, right? And that brings up this final question that we'll be addressing over the next couple of days, which is more foundational in the first place, concepts or percepts? Are percepts the foundation for our thought, as the British empiricists have thought, and the New York empiricists like Jesse Prinz? If the percepts are the foundation, then how do they allow us to bridge what has been called the semantic gap? How do we go from just this perceptual information to our rich and nuanced representations for string, for example, in all of the different ways in which it can play a role in our world? If we're just stuck with a view of string that looks like this perceptual experience, then how can we ever correctly apply string to describe a string of hits or a string of islands? So that is what we mean by the semantic gap. On the other hand, if concepts are foundational, then how is it that they actually reach down to influence these perceptual systems? Many cognitive scientists believe that perceptual systems are these modules. They're running relatively independent of the rest of the central brain system. And if these perceptual modules are really doing their work independently of the rest of the brain, then how can these concepts be reaching back down to influence them? Right? The position that I'll be advocating is that both are true. Both concepts and percepts are foundational. Both are going to be influencing each other. And if you adopt that kind of perspective, then the question is, how can you have this story that doesn't turn out to be viciously circular? Right? How can you have concepts influencing percepts and percepts influencing concepts at the same time? That seems hopelessly circular. It seems like exactly what we're supposed to be avoiding in our theories. What I'd like to convince you of at the end, that it is circular, it's just a benign circle. It's not a vicious circle. Okay. So that's the ground rules for what I'm going to be talking about. Going back to this idea of perceptual information providing a grounding or a foundation for our concepts. You see this as a foundational concept in much of the most productive programs in cognitive science. In phonology, it has been argued that all of the phonemes that we use can be distinguished on the basis of 12 basic perceptual fixed features related to places of articulation in the mouth of sounds, whether it's consonantal or vocalic, anterior, coronal, voiced, or nasal. And the idea is that if you know the perceptual value on these 12 fixed features, then you'll be able to tell exactly what phoneme somebody is trying to say. This general approach of trying to understand cognition by recombining different building blocks, different fixed features and different arrangements has been applied in lots of different areas. It's been applied by Roger Schenck to understanding entire scenarios such as ordering food at a restaurant. And he argues that everything that we need to talk about in terms of ordering food at a restaurant or going to a doctor's office can be understood in terms of 23 basic primitives related to like propel, move, ingest, which is important for restaurants, expel, grasp, P-trans, which is physical transfer, and there's also M-trans, which is mental transfer. And so he's going to be explaining all kinds of elaborate situations in terms of these fixed features. In terms of object recognition, Biederman and his colleagues have suggested representing all of the objects that we know and love, like telephones and flashlights, in terms of a fixed set of geometric features. And here he proposes 36 geons, different types of circles, wedges, cylinders, that can be combined together in different arrangements to create the difference between, for example, a cup and a bucket. And finally, in my own area of concept learning, it's oftentimes been an implicit assumption in the field that the subject's task is not to figure out what are the underlying features for the objects to be categorized. The subject's task is to figure out how to arrange what they know are the features in different arrangements. So here are stimuli that Shepard, Haviland, and Jenkins famously used, where the experimenter and the subject both come into experiment agreeing that these objects are going to be described in terms of their color, their size, and their shape. Right? In fact, this assumption is so strong in cognitive psychology that many cognitive psychologists don't even bother showing what the features are. Right? They just show the abstract representations in terms of ones and zeros. They say, okay, this one object that belongs in category A has a value of 1 on dimension 1, a value of 1 on dimension 2, etc. They don't have to tell you what the objects actually look like because the experimenter and the subject already agree. So what I would point out is that the real world is not like that at all. That if you go outside on a nice spring day like today in Riga and you look at the fields of dandelions, it's a very complicated scene. You don't know what are the features. It's a big cognitive mental leap that you have to do in order to even figure out how you're going to be describing the scenes, right? So the world does not come wearing its featural description on its sleeves. We, during the course of experience with our world, come up with that description. So that is, I think, what's going to make concept learning far more interesting, because you're trying to figure out the features at the same time that you're trying to figure out the concepts. I would like to talk some about research in our own lab on some particular mechanisms that people seem to use to change their perceptual systems in order to better serve the needs of their conceptual systems. And I'm going to be talking primarily about two different types of mechanisms. One mechanism is going to be taking a swarm of visual information and breaking it down into features, or breaking it down into different perceptual dimensions. And the other part of what I'll be talking about is the opposite of that, which is putting together parts of your visual world to create nice units or compounds. All right, so that first side of what I was talking about, breaking down your visual world into pieces, I'm going to call this dimension differentiation. And the best way to understand dimension differentiation is to first understand a different process that occurs in our visual system, a learning process, which is attention weighting. So one of the things that turns out to be extremely important for learning concepts is learning to pay attention to some pre-existing dimensions and ignore other pre-existing dimensions. And in our experiment, we were trying to get at this in a very simple way by giving people different squares to categorize. So these squares would differ on the brightness and their size, and they would simply, during the first part of the experiment, they would simply be shown a square, and they would have to say whether it's a category A or category B. Then we give them feedback on whether they were right or wrong, and then we give them up to 10 days of practice doing this, so they get to be very good at this task. And so these squares differ in their size and brightness. Afterwards, we give them a strictly perceptual judgment to make, which is this square the same or different from this square? In this case, the answer correctly would be different. If I showed you the same square, then the answer would be same. And we're always going to be showing people adjacent squares in this grid. So we'll be showing people those two squares or these two squares, asking, are these exactly the same square along both their size and the brightness? Okay, so that's how the task works. First, you do a lot of category training, and then we're seeing how the category training changes their perceptual skills. And of course, we're going to give some subjects categorization where brightness was relevant for categorization, and other subjects categorization experience where size is relevant and brightness is irrelevant. Okay, here's actually the results from the experiment, and there's black squares and black rectangles and white rectangles. The better somebody is at the task, the blacker the rectangle will be. So if I ask subjects to distinguish between this square over here and this square over here that have exactly the same brightness, and one has size 2, the other has size 3, then this says that after subject has had experience where size was relevant during categorization, they're actually quite a lot better at making that discrimination than they were before they had the training. And the size of this large rectangle suggests that there's quite a lot of improvement at this task for those particular two squares. So what this is, oh, and you would get a white rectangle if people actually get worse, going from before category learning to after category learning. And so you can see there's not much getting worse. There's a lot more getting better than getting worse. So the experimental results for us suggest three different conclusions. First, a dimension which is relevant for categorization becomes sensitized perceptually speaking. It becomes stretched out in your mind's eye. And that means if size was relevant for the categorization that you had to make, then size discriminations get easier for you. And that occurs for this entire size dimension. But the second result is, can you see? Yeah, there's these green circles in the middle, which is to say that this perceptual sensitization is the greatest at the category boundary, right at the boundary between the A's and the B's. And the final result that we are finding is that sensitization of the dimension which was relevant for your task seems to be a stronger influence than desensitization of the irrelevant dimension. In some experiments, we do reliably find some desensitization, some situations where you were better able to perceptually discriminate these objects before you came into the experiment than afterward. But usually we find that it's much stronger effect to get sensitization of things that are relevant. So here, I've asked my friend Joe Lee, who is an artist, to represent some of the mechanisms that are suggested by our experiments using the character from the American Gothic painting. And so on the left, we always have the way that the world looks originally before you have this influence of the experiencer. And on the right, we have how the world looks because of the experiences that we have. And so this first mechanism that I'm talking about can be considered attention weighting, where certain properties of the world, like the drumstick and the chicken breast, become emphasized because they're relevant for the categorizations you need to make. And there's other mechanisms that are also being implicated in these results. One is certainly differentiation, that objects that on the left panel seem to be very similar to each other can come to seem very, very distinctive from each other with training. And that's the difference of like size 2 versus size 3 for a subject who gets a lot of experience. And the final implicated mechanism from the result that I just said is categorical perception. And categorical perception is a widespread phenomena whereby we tend to accentuate the differences between objects that fall in different categories, and we tend to eliminate the perceptual differences, subjectively speaking, between objects that fall into the same category. So there is actually variation among the chickens that belong in coop A versus coop B, but because of the influence of the perceiver, the differences between these chicken coops is accentuated, and the differences within a coop tend to be de-emphasized. Okay, so all of that has to point to this attention weighting mechanism. Where dimension differentiation comes in is that one truism is that you can only pay attention to size rather than brightness if you've already sorted your world into these two dimensions. So you can actively and efficiently pay attention to brightness because in your experiences you've already split apart size from brightness. But there's also this mechanism that I think happens with learning, which is you start with dimensions that were not originally separated, and with training they actually become separated. And there is evidence for this happening developmentally. 4-year-old children actually have a hard time ignoring brightness differences if they're trying to attend to size differences. So for a 4-year-old child, even brightness and size seem to be fused together psychologically. They're glued onto each other. Part of development is splitting them off into different dimensions. And that's been observed also with expertise effects. Burns and Shep have shown that color experts, like vision scientists and artists, are better able to differentiate the elementary dimensions that make up colors. And so here is another kind of experiment that we've done using two dimensions that are considered to be fused for most people. And this is the dimension of saturation and brightness that make up color, in addition to this other dimension, which is the hue itself. So saturation is a psychological dimension that's related to the perceptual dimension of how much monochromatic light have you mixed into the color. And brightness is a psychological dimension related to the physical dimension of the luminance energy which is coming off of a color. And so here I've created a grid of brightness and saturations. And what we find is if we do exactly the same experiment that I talked to you about before, but we replicate it with these dimensions, we find that with more training now, but with several hours of training, subjects can come to be able to make a saturation categorization and ignoring brightness quite efficiently. And when they do so, we find that it accentuates the difference between these two colors, but not between these two colors. So we think that this is a model for dimensions that used to be fused for us. We have a hard time knowing even whether we're changing the saturation or the brightness of something, come to be able to be fused apart. And we've taken this a step further with dimensions that we know are fused together because they didn't actually exist out there in the world at all before. So we can create new perceptual dimensions by morphing between randomly chosen bald heads. Why bald? They're sexier and they actually morph better. Yeah. So we can make a new dimension, which is basically the John to David dimension, by changing in the face how much it partakes of John versus David. The more David is in a face, the less John is in a face. And then we can create another dimension, which is the Sam to Frank dimension. And so the more Frank you have in a face, the less Sam you have in a face, right? And so all of these faces that you see here are going to be half composed out of the dimension A, where they are on dimension A, and half composed out of dimension B. Right? So each one is a blend. If you look at adjacent faces, you'll probably convince yourself that they're exactly identical. But if you look at the opposite corners, you can hopefully convince yourself that the faces are in fact different from each other. Right? If you look at the extremes, you can see that they're different. And what we can do, again, is we can give people a categorization where we split the faces like that. All of the ones on the left belong in category A, all of the ones in the right belong in category B, or for other subjects, we could give them the other kind of categorization. And then we're interested to see how that changes their pattern of perceptual sensitization. The results are, first, the categorization can be learned. Really, it can be learned over the course of an hour or 2 hours easily. But once it has been learned, then that relevant dimension, which didn't exist for subjects at all before, it can become selectively sensitized. So you become an expert at seeing dimension A differences and ignoring dimension B differences. And then once you've learned it, then you find that variation on this irrelevant dimension B difference, for example, is easily ignored. So we think that this is a model for how a child can go from having size combined with color to having them separated from each other. Okay, so this is Joe Lee's take on dimensionalization. Dimensionalization, you start with a world which is unstructured, or without an apparent structure, and the influence of the perceiver is to add a structure onto it. Okay, right? And this is the case for something like our morph dimensions or saturation. There's a special case of this which occurs when the dimensions or the aspects of your perceptual world are spatially delineated parts. In this case, you have a mechanism that decomposes a complex object into parts. And so that would be called segmentation. And so this is, I won't give you the evidence for this, but this is what Joe Lee's take on segmentation is. This is what the world looks like on the left, pre-segmentation, and the influence of the human perceiver is to segment the chicken into parts that have been learned to be important. Okay, so that's all this first part of what I think happens with our perceptual system when it has to engage in a concept learning enterprise. I wanted to now talk at less extreme length about the other side of the coin, which is composing together pieces that used to be thought of as separated and composing them together to create a single functional higher order unit. When would you do that? You would tend to create a unitized representations when you have a coherent, complex pattern of pieces that are co-occurring together, particularly if that co-occurrence is going to be predictive of something, if it's going to be useful for a category that you have to learn. Okay, and so there's extensive evidence for years and years for this happening. Schifrin and Lightfoot, LaBerge have for years have been pointing out that you can become an expert at looking for a particular set of like 3 components together, and if you become a good enough expert at detecting those 3 components, then you basically aren't influenced anymore by how many distractor objects you have to wade your way through, visually speaking. And this is true even if those distracting objects share 1 or 2 line segments in common with the conjunction that you're looking for. Neurally speaking, there's a particular area called IT of a monkey brain, which becomes expert at particular views of objects if they've been exposed to the monkey oftentimes enough. So what Logothetis and his colleagues did is he took a particular view of this wireframe object and he showed it repeatedly to this monkey. And what came out as a result of this is that this view would become very successful at triggering particular neural cells in this area of the inferior temporal cortex. If you slightly rotated the wireframe, it wouldn't result in nearly so much cell firing. So you get particular cells in this visual area, not the primary visual cortex, but 3 or 4 synapses down from the primary visual cortex that become sensitized to these very well-learned views. In this case, it was 10,000 trials. So some of this takes quite a long time. Isabelle Gautier, Mike Tarr have done a lot of studies involving these Greeble figures, where if you expose subjects to just one of these Greebles oftentimes enough, it becomes something like a chunk, a unit. And people become very able to detect it. But if you flip it upside down, for example, then people go back to how they were with just regular old other non-familiar Greebles. One of the most unitizable types of stimuli out there that everybody knows from your day-to-day experience is the unitization of letters into words and letter fragments into letters. So going back to Cattell in the late 1800s, we've known that words that are sufficiently familiar to us become unitized. And Cattell's evidence for this is that it doesn't matter how many letters were in a word. If it's sufficiently familiar to people, people can recognize a 10-letter word just as fast as they can recognize a 4-letter word, because we have no longer a processing of the individual letters, but we're processing as a single whole unit. Okay. And in our own lab, we've given people an awful task. This requires something like 10,000 trials. But we give them one object that belongs in category 1. I'll call it A, B, C, D, E, where each of the letters corresponds to a particular bit of this blob. Right, so I'm adding the chunks for you. And all of the near neighbors to it belong in a different category. So all of the near misses, like A, B, C, D, Z, belongs in category 2. And A, B, C, Y, E belongs in category 2 as well. So in order to reliably categorize something as a category 1 object, you really have to pay attention to this full 5-way conjunction of A, B, C, D, and E together. This can be done. It takes subjects, like I was saying, there's continued improvement over 10 hours of training in this task. But once they've been trained at this task, they're very efficient at being able to spot their new friend, A, B, C, D, E. And there's good evidence that people are responding to it just as fast as they would be able to respond to just a single component like A or C. So I'll save you from the gory details here, but the bottom line is that by looking at people's reaction time distributions, we're able to say that when they're finally able to respond efficiently to A, B, C, D, E, they're able to do it without breaking it down into its individual components of A and B. If they were doing that, they would be far too slow. Okay. So that's what all right. So I'll instead of giving you the data, I'll give you Jolie's visual rendering of it. This is his process take on unitization, where if you had a reliable, this doesn't exactly work, but if these chickens were always in this particular configuration, and if that configuration were important for the farmer, then the farmer would tend to unitize them into a single chicken form, right? So that is what the unitization mechanism is doing. So by way of wrapping up, one of the things that I wanted to suggest is that these two different mechanisms that I've been talking about, they seem like they're diametrically opposed in some ways. So which way is it, Professor Goldstone? Does training cause you to take your world and break it down into pieces or parts or dimensions? Or is it the other way around? With training, with learning, with experience, with concept learning, you learn to build up bigger and bigger perceptual units? And my answer is yes, that both processes are going on, and they're really both flip sides of a single underlying mechanism. And we've been very interested in building neural network computational models that we think embody this basic mechanism. So the particular kind of reconciliations that I would try to propose is that both differentiation and unitization are creating appropriate sized units given a set of environments that you have and a set of tasks that you have on those environments. So differentiation occurs if you have components that are varying independently of each other and if they're differentially diagnostic. If, like, my right hand is diagnostic for categorization, but the left hand is not. That's the perfect situation for getting differentiation of those components. Unitization will tend to occur if these components are going to be varying together, and that's unsupervised. You don't need any teacher or rule book telling you that. You can pick that up just from the statistics of the world itself. But in addition to that, if the conjunction is useful for you, is diagnostic of categorization, that's when you're going to get even more unitization occurring. And both of these processes have been implicated as going on at the same time with infants learning how to combine syllables into words. So it turns out that children are very adept statistical learners and very good at being able to, just on the basis of internal probabilities, being able to say that these syllables join together to create a word. So it turns out that this takes place by two things going on at the same time: splitting apart different syllables if they don't predict each other, and combining together syllables if that conjunction is reliably predictive of words. So, and like I said, I'm not going to be presenting the neural network component of this, but we've got, and it would have been good from the rhetorical perspective of showing that this can all work out in a way that is not viciously circular. But we've developed neural networks that process input streams that are coming in, and as they're processing those input streams, they are trying to segment the individual visual objects using some Gestalt laws of perceptual organization. Like pixels will tend to be put together if they're close to each other, if they have the same orientation. And as the system is trying to segment individual pictures, it's also going to be looking for segmentations that apply across all of the different pictures that it's trying to understand. And within this world, what we're trying to argue is that you don't have to start with these features pre-wired into the neural network. The eventual organization, these are the learned detectors that the neural network eventually creates with the input patterns that are shown up here. And the learned detectors aren't there in any sense fixed a priori, but they are coming out as a result of the experience that the network has. And it turns out to be important that it's going to be creating these detectors based upon their categorical relevance. You are going to tend to have a bias towards creating detectors that are useful for explaining the categories that the world is providing it. So if there is a category of A things that tend to have this antenna at the top, then the network will be very likely to create a detector for that antenna at the top. So what we're trying to say is that you don't just have to have selective attention to pre-existing features, but you can also have selective attention to features that you are creating yourself. And that seems to be true for us neurophysiologically. Okay, so what I think at the final analysis, what we're arguing for then is that people will naturally create new perceptual representations during category learning. What I was just saying, that this vocabulary, if you will, of perceptual units need not be fixed a priori in order for selective attention to occur. You can think about these perceptual units as basically involving a repackaging of stimulus components. Creation of features does not mean anything goes. There are strong constraints on what new vocabulary elements you'll be creating. There's perceptual constraints that you tend to create features that are going to be connected to each other, having similar orientation, and part of good closed objects. And you also have these category relevance constraints that you tend to create these pieces exactly because they're relevant for the categories that you need to learn. One idea that I'd like to propose is that if you have a sophisticated enough brain mechanism for creating new perceptual representations, then you probably don't need to have a very sophisticated mechanism for deploying these fancy rules like you belong in my category if you're square or triangle and white or pink, right? And I think those kinds of categories are actually pretty hard for people to learn. I think it's much more likely that people learn categories by creating simple perceptual features rather than elaborate logical concatenations of Boolean operators. So I do think that conceptual and perceptual learning mutually influence one another. It's a benign circularity. This is one way of thinking about it architecturally by comparing the old Bauhaus school of architecture to maybe new architecture as embodied by the works of Frank Gehry. Right? So the Bauhaus school was trying to build everything out of these primitive building blocks, right? These circles, rectangles, and triangles. Whereas a big part of what makes Frank Gehry's building so interesting is that he's very interested in creating new vocabulary, new structures, while he's trying to create the buildings. And finally, I'll let Joe Lee have the final illustration here. So what we're trying to argue is that we learn from our experiences in the world, but then we turn around and we interpret the world exactly in terms of those experiences that we've had. Okay, thank you.
Now time for a question. Any questions, comments, or anything to add?
Yeah.
Hi. I have a question about when you're talking about experts and you're saying that they are able to distinguish like some basic things that fall into some categories so they can make assumptions and do some cognitive stuff with that. And the question is about, can you unlearn it? It's like you spend so much time to learn this useful stuff, and then at some point you think that oh well, this doesn't work anymore. Yeah. But can you like do that easily? Like
right. Right. So this is the dark side of being an expert, is that you may be constrained in terms of how you're viewing your world exactly because of the expertise that you've developed. And we know all of professors who can't help but see the world in terms of the theories that they've developed, even though maybe their theories aren't exactly the most aptly applied in this situation. Psychological evidence exactly shows that phenomena. That, for example, if you've spent a lot of time becoming a 3 expert, looking for 3s in displays that have lots of digits in them, now you switch people to a task where they now have to look for 7s. But sometimes you put a 3 in there. People who have become these 3 experts are very distracted by those 3s, right? So it's exactly this kind of attentional capture that it is automatic and you can't turn it off. And this is particularly important in educational contexts, I believe, because one of the things that teachers who hopefully are experts at the topics that they're teaching oftentimes have is what's called this expert blindness. They have a hard time understanding what the world looked like to them before they acquired their expertise, which is problematic if they're trying to get in the mind of the student. They can only see things. How could you not see that this is a situation where you'd have to apply the second law of thermodynamics? It just looks like it, right? And so a big part of training is not training the student, but training the teacher on how to look at the world again with the eyes that they used to have when they were the child. Yeah.
Hello, thank you for the lecture. I have a question, not so much on cognitive, but I come from a development background, so I deal a lot with inequalities, and I wanted to ask you, how would you then explain, then according to this, if a person is not an expert, it's completely normal that he or she is intolerant, like racist or homophobe or something like that? Would that then... Yeah, how would you explain that? Then, for example, if it's such a unified society, then is it considered normal until the person becomes an expert to be intolerant?
Yeah, I mean, so part of me would answer that there's a sense in which expertise comes with it, a vantage point. You're looking at the world from the particular perspective of somebody. And so it has with it this idea that we are going to be discriminating, right? And so I think what we have to do is, as a cognitive scientist, not try to get people to stop discriminating, but rather to get people to discriminate on the basis of legitimate grounds rather than illegitimate grounds. So, you know, it's actually good that we're discriminating to this rattlesnake. You know, so we see this rattlesnake coming to us, and we say, oh, well, I know that other rattlesnakes are poisonous, but I'm not going to hold that against you. Come here, nice rattlesnake, pat, pat, pat. That would be non-evolutionarily viable for us. So I think we do need to discriminate. So I think the problems that come in is when we discriminate on the basis of these superficial features like skin color or religion that are not actually as inductively powerful concepts as we tend to think they are. So I think a big part of expertise is trying to get people to pay attention to really what is the proper discriminanda. So as a cognitive scientist, I mean, so it sounds kind of negative, but I don't think we should be trying to make ourselves less discriminating. I think we have to find the right features in order to do that discrimination.
Any other questions, short comments, or?
Does your work has implications on early childhood learning? For instance, one of things that come in mind is differentiation between letters and syllabus and words. And the kids usually have a hard time to jump from letter concept to word. And it seems, it feels like that we fail to understand how this happens on brain, and because of that children develop reading ability kind of later than actually they could be capable of.
Yeah, that's a good question. So I know how that plays out in America, and I don't know whether it's the same in Latvia, but there's of course these pendulum swings of teaching methodologies, particularly with respect to reading, teaching reading. And right now, America is definitely in the grips of the whole word method, where we're trying to say, oh, you know, these individual letters are only very imperfectly connected to phonemes. It's best just to learn the entire whole word. And this is enmeshed in a bigger practice to only give people meaningful texts to them, what they call authentic reading materials. It would be considered wrong or maybe even unethical to give them texts that said, Ned is red, Ned is in bed. You know, texts that are supposed to exactly be showing you some correspondences between the letters and the sounds they make. That's very opposed to, in America, how things tend to work, which is just get the entire word. And so to my ears as a cognitive psychologist, that's really far on the unitization extreme of things. And it ignores the fact that sometimes there are some regularities that you would get at by a differentiation training. So I think I would argue that America's gone too far over to the whole word method. For low frequency words, it's very useful. For names of countries, names of people, the whole word method is maybe the only way of getting kids to learn it. But for many other materials, I think it's better to actually give people differentiation training too, to see what are the parts and what are the significance of the parts for the sounds.
Thank you. Any other questions or? Okay.
I want to ask how it's possible that people in dreams can see things that they are never seen before.
Did you say people in dreams, did you say?
Yes, people, no, in dreams or something like dreams.
So I would argue that you're getting that because you're recombining building blocks that you've learned before. So you've never seen a whale with a bow tie with 5 legs, right? But you might have a dream about that. But it's a dream which is created because you've gone through this process of creating the building blocks, and then once they're created, then you can rearrange them in different ways. So where I'm differing from Biederman's Geon theory or what I was saying with Jakobson with phonology is that I think that just because something is a building block doesn't mean that it had to be innate or that it always had to be there. So I'm saying that this bow tie thing now acts as a building block that can be recombined with whale and 5 legs, but it didn't have to be born in. You can create the building blocks and you can rearrange them. So I'm totally happy with the cognitive science position that we get our flexible creative cognition through recombining these building blocks. The only point of contention that I have is whether these building blocks are innate.
Okay, thanks a lot. Is there any final question or final comment or?
Hello, I have a question about the dimension differentiation and unitization, and my question is whether can these two concepts exist simultaneously within a perceiver, as in can two presets be created in one mind that, for example, in one set of circumstances I see these dimensions as unitized, and in another set of circumstances I see them as differentiated?
Yeah, that's a good question. I think it's possible that you can see both the entire unit and both the building blocks. I think that's a big part of an artistic or a scientific sensibility, is being able to flexibly go between these levels. But I also think that there is a sense in which there's a competition between these levels of looking at something. So that it's been shown, for example, that in word perception, that if you have a very high frequency word, it's hard to get at the pieces. So it's hard to find the F in the word of, because of is so high frequency compared to frog, or a word that has less high frequency. So yes, I think that particularly somebody who has a kind of trained expertise where they have to go between the levels is exactly the way that you would get somebody to be able to flexibly see the whole and the parts. But I'm guessing that there will always be a sense in which these different viewpoints will be competing against each other.
But so then it would be a matter of training of sorts still.
Exactly. So, right. And so you could imagine training programs that would do exactly what you're doing, and they would feature different blocks. One where the pieces would be composed together and it would be useful, and another where they would be split apart and that would be useful.
Thanks.
Yeah.
Thank you. Okay, there is another final question.
Yeah, take your picture.
Thank you for your lecture. The question is about the other I understand you are talking about the visual senses that we perceive in a space. Can we categorize in the same way also the other senses, smells, sounds, and touch?
Yeah, absolutely. So I think there's been a lot of excellent work on speech perception that has implicated exactly these same mechanisms for auditory information. The best work on categorical perception comes from speech, so that we really have a hard time distinguishing between different allophonic variations, different p's, aspirated or pre-aspirated, if they're all interpreted by us as p's. And that's something that is, because we get so much experience with speech, it seems to be something where it's virtually impossible to make a discrimination between these sounds that are really different from each other. Which is why Japanese have a hard time learning the RL distinction in English, and why English speakers have a hard time having the Korean distinction between pre-aspirated and unaspirated p's, for example. So I think, yeah, so I'm guessing that many of these things also show up in audition. And I mean, I have to say that it's an interesting sociological trend, but probably, 70% of all work is in vision, and the remaining 29% is in audition. And taste and smells, there's 1%, so it's really unknown lands, terra incognita. So I hope that some of you will go off and look for these things in the other less studied senses too.
Okay, thanks a lot for questions. Thanks a lot for the challenging speech, and see you tomorrow.